Hi everyone, I'm Andrea Bernardi and I'm a master student at University of Modena and Reggio Emilia. I'm glad to be here to present paper called an FPGA overlay for efficient real-time localization in 1/10 scale autonomous vehicles. Before getting to the heart of the presentation, I would like to make a quick introduction on what is F110 project. F110 project is autonomous driving competition of 1/10 scale race cars. This held between universities around the world. We think F110 project is a great way for students and young researchers to approach and learn autonomous driving solutions. In our laboratory, we currently have a team working on the main prototype that is based on NVIDIA TX2, but the rise of research interest on FPGAs brought us the idea of creating a second prototype based on the Ultra 96 boards. Research on FPGA is interesting for the many advantages over traditional accelerators. For example, we are able to deliver a better performance path compared to GPUs. And the topic of energy efficiency is a central topic on embedded systems like autonomous vehicles. FPGAs are also potentially more predictable platform. This is important for the timing constraint of the autonomous driving. Finally, another advantage is the level of abstractions closer to the hardware that permit us to reduce the end-to-end latency of the driving stack. As I presented on the figure on the right, FPGAs outperform CPUs and GPUs in terms of power consumptions. In this sense, ASICs present the best power consumption. However, the amiable programming framework and the flexibility in reconfiguring the design that FPGA offers demonstrate its applicability and effectiveness in the development of autonomous driving applications. This as a preliminary pre-production system in contrast to the ASICs. Considering this benefit, autonomous driving on FPGA seems an appealing research topic, and the F110 environment is a perfect trade-off between researching on a simulation and doing it on the real vehicle. Thanks to the F110 environment, we are able to test our algorithm safely and in a context that is very close to the real one. In particular, the algorithm concerning our research are tested on two main boards, Ultra 96 and ZC102. Both of these boards are based on MPSoC Zinc UltraScale Plus, where the processing system part is equipped with 4 ARM Cortex-A53 and 2 ARM Cortex-R5 mainly. What differs these two boards is the programmable logic. In particular, the Ultra 96 has a smaller programmable area than the ZC102. What you can see now in this image is our current F110 and autonomous vehicle stack. The main component, as you can see, is the LiDAR sensor that is used to localize the car in a known map through a Monte Carlo method called the particle filter. The optimal path can be statically obtained by a path planning algorithm, and the control loop is closed by a well-known purposive algorithm. So the first question we asked ourselves is what component of the driving stack we need to put on FPGA to improve the stack. We have a main problem. Running the driving stack shown in a previous slide all on the processing systems of the boards, we noticed that the localization was lost. This is due to the high computational cost required by the localization algorithm and not supported by the processors. So at the question where to use FPGA, the answer was to be able to try put part of the localization algorithm of our F110 stack on FPGA. As a localization algorithm, as I just say, we use a particle filter. This is a Monte Carlo type algorithm that gives an approximation of the vehicle's positions. The particle filter is composed by 5 functions that you can see in the image on the left. In particular, these 5 functions are the resample function that have the task to generate high randomly number of particles that are represented in the image on the right as a red dot. The particles represent the positioned candidate and are expressed in form of poses x, y, u. Next, we have the motion model function that updates the particle poses this respect to the odometry information coming from the low-level MCU of the vehicles. This data might not be accurate, and typically Gaussian noise is added. Next, we have the remarching function that creates 60 rays centered in each particles. They represent the hypothetical point cloud, the fake point cloud, as seen from the center of any particle. And this algorithm calculates the distance between the particle and the track boundaries for any radial rays. This process is iterated for any generated particle. Next, we have the compute weight function that associates a weight to each particle, this depending on how much the fake point cloud matches the current representation of the world, in other words, the real point cloud that the LiDAR sensor see. And finally, we have the normalized that have the task to normalize the weight to be in the range of -1, 1. So now our contributions are divided into main parts. One is the creation of IP core to have an hardware acceleration of the particle filter algorithm. And the second is the use of proxy core to decrease the data transfer. We will talk about these two aspects in more detail in the following of these slides. Now, by profiling the fine function that composes the particle filter, we notice that the remarching function occupies more than 80% of the execution time of the entire particle filter. So the natural consequence was to bring the remarching function on FPGAs, in other words, create an acceleration hardware of the remarching function. In particular, we have created an IP core called the remarching engine, which communicate with the rest of the particle filter function through a DRAM memory. The communication is happen with three Axie master interfaces that are the map reader port for initializing the map, the part reader port used for reading the particles from the DRAM, and the rays writer port used for write out the calculated rays. The main internal component of the remarching engine are a map loader used for initializing the shared map memory, and this process is done only once at the boot of the systems. Next, we have a multi-bank shared map memory that is used for storing the map of the environment. We have a parametric number of processing elements that in the image are represented as a black blocks named RM0, RMN. And this processing element executes in parallel the calculation of a ray for a single particle. And finally, we have a particle reader and the rays writer that is used for dispatching and collecting input and output data. Now, by applying the remarching engine, we had the first results. As you can see from the image, we are now able to maintain the localization and close the trajectory path. In addition to this, we are able to reach the maximum trajectory speed for both ZCU102 and Ultra 96, even with larger maps. And this therefore gives us the opportunity to be more competitive during the F110 races. If now we look at the trend of the velocity graph, we have a sort of Gaussian trend. In particular, in the left side, where I still have a few particles, I couldn't have a good localization, so the speed I support will be low. On the other hand, on the right side of the graph, I have too high number of particles, and therefore I have high computational cost of the particle filter algorithm. So consequently, I don't have optimal localization. So given this Gaussian form, we have a trade-off between speed and number of particles. From the point of view of this type of research, the area of interest is that between 16 and 80 particles. In this area, I can compare the three proposed configurations at the maximum algorithmic performance. To get the graph of velocity, we use a simulator. There are a number of simulators to support the design of autonomous vehicle systems. In our case, since we target the 1/10 scale vehicle, the natural choice is to use Office Simulator of the F110 project. This is the simulator that we designed to setting up the stack before the races, for example. This simulator accurately reproduce the environment, the map, and the sensor data. The simulation that we choose is, in particular, is an hardware-in-the-loop simulations, which means that we deploy the software stack component written in C++ directly on the final board that we also use on the vehicles. Using this method, we can calculate the maximum and the average speeds of the vehicles as the particles vary. In particular, having a fixed number of particles, we carry out several tests by varying the speed. This until the vehicle crashes into the bound of the track. When a crash occurs, it means that the localization has been lost, and the maximum speed for the fixed number of particles is the one given by the test immediately preceding the test where the crash happened. This process was done from 10 to 2000 particles. With this type of method, we have made some tests on a different type of maps that vary according to the size of the track. In particular, beginning on the left, the first circuit is the circuit we have assembled in our laboratory. The second and the third are circuit actually used in F110 races, respectively in New York and Montreal races. And the last circuit is a circuit that does not exist in reality. But as you can see, this circuit is bigger than all the other, and this serves us to test the behavior of the particle filter in larger maps. Now we have a localization that works also for FPGA based boards. But how much costs remarching engine in terms of offloading of data in DRAM? Doing some calculation, if we have 80 particles, that is the worst case in our area of interest, and every particle has a point cloud formed by a 60 rays as a type float, we have a offloading in DRAM that is 90.2 kilobytes. This writing is done with the LiDAR frequency, so the remarching engine writes 90.2 kilobytes every 30 Hz. So what can we do to reduce this offloading? In other words, how to make sure that the data written in DRAM by the programmable logic is less than 90.2 kilobytes each time. What we would like to do is to take the compute weight function, the function next to the remarching function, and put it on the FPGA. In other words, create an acceleration hardware of the compute weight function, as to bring it closer to the remarching engine. Unfortunately, we cannot accelerate the compute weight function and put them on the programmable logic. This because, as you can see from the table shown in the slide, from the ZCU102, for example, we don't have enough VRAM and LUT to obtain a good hardware acceleration. To resolve this problem, we use a softcore. The proposed overlay design that you can see on the left is composed of three main components. One is the remarching engine, another is the RISC softcore deployed on the programmable logic, and finally we have a shared scratchpad memory local in programmable logic. This scratchpad memory is used as a data memory for storing recurrent temporary buffers. Our prototype Proxy core is excelling Sublaze microcontroller, and this is an open source course such as RISC-V course. The Proxy core is programmable, and this allows us to optimize the area on the programmable logic, because we do not have to offload the IP core of the compute weight, but we can run them over there, over the Proxy core. With this configuration, the Proxy core enables the offloading of the compute weight stage into the DRAM and removing the need to move data out of the remarching engine. If we rerun the example that we have done before, now notice that the offloading in DRAM is only 0.32 kilobytes, in contrast to the 90.2 kilobytes that we had before. In this slide, I represent a breakdown of the particle filter, and you can see how our design enjoys the benefit of hardware acceleration with minimal data transfers. This thanks to the adoption of the Proxy core and shared VRAM banks. With this design, we further improve the end-to-end performance of the particle filter by a speed up of 2 or 3. This compared to a design with only remarching engine. In conclusion, in this work we proposed an original system design for a next generation automotive domain controller. This based on reconfigurable embedded accelerators, such as, for example, the Xilinx UltraScale Plus SoC. With our design, one can deploy computational intensive tasks for autonomous driving system efficiently and scalable, with high degree of flexibility and power efficiency. A final important thing to note is that we know that the design of remarching engine can be improved, but is not what we want to demonstrate with this paper. Instead, the primary outcome is that the design we propose has a good software scalability and potentially allow us to have more predictability than CPUs and GPUs. Furthermore, the architecture present is a rigid architecture, and this gives us the possibility to create specific programming models. This is highly requested in a context such as autonomous driving, but more in generally in real-time applications. I'm finished. Thanks for your attention, and for any question I will be happy to answer it.